In the last video, we introduced the whole idea of regression models, and modeling is a very valuable way of capturing the essential relationships between what you might describe as causal variables and outcome variables. So there are outcomes that you want to control, and there are variables that you might have some control over that cause those outcomes. And so if you can adequately describe the relationship between the causal variables and the outcome variables, then you can start to plan on what actions you might take, the ways you might influence the x's or determine the x's in order to influence the outcomes amongst the y's. So we're into a world of great potential. We're doing the most simple kinds of models, which are these linear models, but we are making it a little bit more complicated by allowing the possibility that we've got multiple x's. And that's built on the idea that no one outcome is a result of one influence. There are many influences on a particular outcome, so our model has to have that characteristic for it to be useful to us. Okay, so we've, in the previous video, introduced the model. We've talked about how you interpret it, how you just check whether each of the x's are relevant by doing a little hypothesis test, looking at the p-values. But we also need to think a little bit about how we evaluate whether we have a good model at the end. And then also, later in this video, we're going to think about how to generalize the model a bit to different types of x's as well. So first of all, the evaluation task. How good is my model? Well, there are basically two things that you're going to use from three things you're going to use from your Excel output that help you to assess whether you've got a good model or not. The first one of those is something called R squared. And R squared is actually essentially a variation on a correlation coefficient. So it's the correlation coefficient, or particular correlation coefficient squared. And if you remember what a correlation coefficient was, it was a video few videos ago. It's a number between -1 and 1 that measures the strength of the relationship between an x and a y. And a correlation of basically 0 says there's no relationship. A correlation near 1 or -1 indicates a very strong relationship. What we do with R squared is we take that correlation between the y and the predicted value of y. And so, again, if that's a very strong correlation, that's good news. It means that the predictions are close to the true values. And we square it so that the minuses become positives. And then we just ask the question, how close is this quantity here to 1? If it's close to 1, you've got a very good model. If it's close to 0, you've got a pretty lousy model. There's not much correlation if it's close to 0 between what your model predicts for y and what actually happens to y. Okay, so in our Excel output, we just have to have a look at the R squared value, and here it is in this particular example here, 18.36%, and interpret that in relation to that range between 0 and 1. And the first pass, you look at that and say, well, that's a fairly low number. 18% is not great. It's not perfect. There's still quite a lot of, in fact, there's 80% of what's going on here is not explained. There's only 18% that is explained. So we haven't done particularly well, but in this particular case, something like explaining wages of individuals is quite difficult. So I guess a little bit of experience in doing this allows you to know what's a good R squared and what's not a good R squared when you're looking at this cross-sectional type of data like this, where you're looking at the behavior of individuals. How much money does this person earn versus that person? It's actually really hard to get a great model, and so you can be quite happy with 18 or 20% R squareds. In other cases, if you're perhaps modelling something that's a bit more stable and predictable, you might be looking at 90-something% R squareds before you're satisfied. Let's just go back a little bit to this technical bit here to interpret what the R squared is actually measuring, and it's probably best done visually. Remember, you're fitting a line through some data, and if we've drawn this picture here in terms of as if this was the simple regression model, got a y here and an x here, and the intuition is best explained with just simple regression. So the R squared, or the error in the model, is the difference between what the model predicts and what actually happens. So what actually happens is the dot. What the model predicts is the line value. That difference is the error. And so what the R squared is doing is measuring essentially the proportion of the variation from the mean that is explained by the model. It's basically the explained sum of squares on the total sum of squares. So how much of the variation in y has x been able to explain? That's the explained sum of squares, and that dividing by the total variation in y makes this into a proportion so that it can be expressed as a number between 0 and 1. So when I get in the next page here an 18% r squared, I'm saying that I've explained 18.36% of the variation in y with this x variable, or this, in this case, this set of x variables, education and age. So 18% or over 18% of the variation in people's wage income can be explained by their level of education and by their age. That's how we would interpret the r squared. Okay, so as I said before, that looks fairly mediocre, but we know from experience that actually modelling wages, that kind of individual level outcome, is very difficult, so it turns out that that's not too bad an outcome. That's our first means of judging whether we've got a good model. The second one is this quantity here called the standard error. And the standard error is essentially related to the error from our model. Go back to this picture here. Remember, these quantities here are the errors, the difference between what actually happened and what your model predicted would happen. And what the standard error does is it calculates the standard deviation of those errors, squares them, adds them up and divides by n-1, and then takes the square root. So that's the formula there. Actually not n-1, n minus k minus 1. You've got to adjust for the fact that you estimated quite a few slope coefficients here, k of them in fact, plus an intercept. So that's the formula for the standard error. It's just like a variance formula that you're used to seeing. Remember, the error is at the mean of 0, so it's the sum of the errors minus their mean, which is 0, so it's just the errors squared, divided by n minus k minus 1. So that's a variance. Square it, you get a standard deviation. So this is a standard deviation of the error term, and it's an indication to us of how much error you typically make if you were to use this model to predict y. So if I was going to use this model to predict what someone's income was, how accurately would I be doing it? And on average, I would be in error by $32,535 in this case, dollars. Now, that doesn't look too great. I forget what the actual data told us the income values were, but this is annual income, so it might be sort of $80,000, $100,000 or thereabouts. So if you've got, sometimes people earn more than 100, sometimes a lot less than 100, but it's around about that kind of range. And if you've got a model that can predict your wage with an error on average of $32,000, you'd have to say that's a pretty poor predictor. So if I was trying to predict, for example, I've got a model for predicting how much the sales of our business is going to be, and the sales are very stable. There's very little variation on it on a day-to-day basis, and perhaps we're running a shop that sells ice creams, an ice cream shop, and the outcome sales depends on X, which is the temperature. Hot days we sell a lot, cool days we don't sell very much. And suppose it's really a very predictable thing. So if you know the temperature, you can predict sales with a great deal of accuracy. Then when you fit your model to it, you should expect your errors to be on average quite small. But on the other hand, if it's a really difficult thing to predict that people's ice cream consuming behaviour is very volatile from one day to the next, and it's not just dependent upon the weather, then you might find your errors, your standard error is quite big, that your average errors are quite big. So there's not a black and white way of saying what's a big standard error and what's not. But in this case, we've actually told here that the average wage was $33,000, and we're predicting the wage of an individual based on their education level and their age. And on average, we're going to be wrong by $32,000 above or below. That's not very good. So that's a pretty poor model, you have to say, at that point. So that's our second means of evaluating our model. We can also evaluate the model just by looking at the errors that we got and have a look and see if there's any sort of pattern in those errors. The errors we get by comparing the actual data points with the data points on the line. So you can imagine constructing a plot of the residuals like this thing here, which essentially says These dots above 0 indicate that the actual value was bigger than what the line predicted. These ones down here say the actual value is smaller than what the line predicted. Now, if you get a bit of a random pattern to the residuals, that says, okay, the model may not be perfect, there's errors, but there's no real obvious pattern to those errors, so it's not as if there's something left unexplained in the patterns in the data. So you'd say that's the model that produced this set of residuals is probably not a bad model. Over here, the residuals follow a very clear pattern. They're all heading up for a while and then all heading down for a while and then back up. So that suggests there's a pattern in the residuals, which means there's something about the model that's inadequate. You've left something out. The idea of a model is it should explain all the patterns, and what's left over should just be random. You can't explain randomness, but you can explain patterns, or you should be able to explain patterns. So if this is the residuals you get, you'd have to say there's something not quite adequate about your model. There's something missing in your model. Okay, so that's your third kind of tool at your disposal to help you evaluate whether you have a good model or not. Now, in fact, one of the things that the residual plot will show up for you is if the relationship between x and y is not linear, then if you stick a straight line through this data, you're going to get a pretty dodgy looking set of residuals. In fact, this one here comes from a model where the relationship between x and y is not linear, and you get this consistent pattern here. So one of the causes of this pattern could be that you just missed out an important variable from your model. Another possible cause could be that the relationship is not linear. This is an example here where what you get is countries which have got higher incomes, richer countries, tend to have fewer child deaths. They tend to have better health services and everything else, and so children die at a much lower rate. Poor countries have a much higher rate of child mortality. But it's not a nice linear pattern. You find that as your income levels increase from sort of really poor to middle income, there's a dramatic improvement in the child death rates. But then when you go from middle income to rich, the improvement in mortality rates of children is relatively small. So it kind of improves dramatically at the start and then slows down. So a straight line through this data is not going to do particularly well. How do we deal with that? Well, there's a whole world of models that you can fit which are not linear to cope with this kind of thing. And that's the sort of stuff that if you do later studies in statistics or data analytics or econometrics, you'll come across some of these. We've got one simple solution now, which is a bit of a trick that we play because we're only working with the multiple linear regression model, but we can include our x variable in some nonlinear way in order to create the resemblance of nonlinearity in our model. So we include not only x but x squared, and that allows us effectively to imagine, instead of fitting a straight line here, to fit a quadratic function. Now, quadratic may not look that sensible here, but if you imagine a quadratic's like a U shape, goes down and along, and then it might go back up again, which isn't very realistic, but you don't care about that because you're not actually using the model out here for really large values. So the quadratic that goes down and curves around and goes back up, for the area that you're actually using it for, could be quite reasonable. So if I was going to estimate a model like this, I would need to add another column to my Excel spreadsheet where I take the values in the x column and I square them. So just equals x squared, so equals a, if this is in column A, this is in column B, B1 equals A1 squared, B2 equals A2 squared, and so on. Stick them all together. Run a regression with this as my dependent variable and these two columns as my explanatory variables, and I get this result here. And you'll see, sure enough, that not only is income significant, p-value is very small, but so is income squared. So that says that there's not a linear relationship here, but there's some sort of quadratic relationship between these things. Makes it a little bit hard to interpret these coefficients, and we won't worry about that for now. Certainly not too difficult to use it for prediction. So if you said if you've got a country with a particular level of income, you plug in the income value into the model here and the income squared value in here, and you can predict what their infant mortality rate will be. But interpreting the coefficients in the usual way is a bit difficult. Okay, so that's the first extension you might want to do. So you've got a model which your residual plots have suggested to you is not linear. You can do lots of things. For now, the one thing that we have talked about doing is just by adding a quadratic term. What about if I've got a categorical variable here. So instead of, so far the examples we've got have been, for example, education and age, which are continuous variables. Okay, education can take a number of years of education, can take many different values. But what about if I believe that people's wage depends upon whether they're male or female on their gender? There's a widely held view that women tend to earn less than men on average, even if they're doing similar kinds of work, just for a whole lot of reasons, partly historical discrimination. So it'd be great to be able to throw in some kind of measure here of the difference between incomes of women and men, and see if we indeed confirm that with this data that women are actually earning less. So what we do to do that is quite straightforward. We just construct a dummy variable, which is a dummy variable is a variable which equals 0 if you are, in this case, it's a female dummy variable, so that means it's 0 if you're not a female, and 1 if you are a female. And we've, I think in previous videos, we've constructed variables like this. When we throw that in the model, so this kind of variable is what's called a categorical variable. The variable is not a measure of how many years of schooling have you had or what age you are. It's a numerical representation of two different categories. No or yes. Not female, female. 0, 1. So we translate those not female, male categories into variables, 0 and 1, and then we put that in our model. And this coefficient here now tells us what would be the difference in income between females and males on average, and it's $7,300, for two people with the same level of education and the same age. Now this starts to get really powerful, doesn't it? Because you can imagine people coming along with the following. They say, oh, look at this, you've got the average wage for women and the average age for men. And you see a big difference between the two. You say the women are earning a lot less than the men. So you say, there you go, there's discrimination. But then some smart person comes along and says, oh, maybe they earn less because of discrimination. That could be right. But it also could be that they earn less because women have got less education than men. They don't go to university as much. And so when you think it's about discrimination because they're women, maybe you're wrong. Maybe it's just people with less education don't earn as much. So we end up kind of rejecting the gender discrimination explanation. Well, we can actually examine whether that response is valid or not with our multiple regression model. We can include both education and gender, and for that matter, age, in our model all at once. Now this number here, minus 7312, says take two people with the same level of education and the same age. So now we've got a woman and a man who have both been educated the same amount of times. They've both been to uni or both finished school or whatever. One's a female, one's a male. This says that the female will earn $7,000 on average less than the male. Okay, so you can't blame the difference here on differences in educational level of men and women, because we've included education in the model, and so this interpretation is based on the situation where this is the same for the male and the female. So that's the beauty of multiple regression. You can eliminate one possible explanation for the difference in incomes between men and women by including that other variable in the model. So that's pretty cool. Just out of interest, what about if I constructed a different variable equal to 1 if you're a male and 0 if you're not a male, which in the case where we've got binary gender selection means that it's kind of the opposite, isn't it? Before we had a 0 for males and a 1 for females. Now we've got a 0 for females and a 1 for males. Stick it in my model, and look what I get. 7312 there. Just go back to the previous one. Look, it's minus 7312 here. Because remember, this was the difference between females and males, and we're saying females are 7312 less than men for people with the same level of education and age. This is the difference between males and females. So if women on average earn 7312 less than men, then this statement says men on average earn 7312 more than women. So it's the mirror image statement, and it's exactly what we should have got, having control for education and age. So that's just a little thing you get. Okay, so two categories, easy to do. Just put in some zeros and ones in a column, add them in, and then your interpretation is as we've just been talking about. Okay, male wages on average are higher by 7,312 for two people with the same level of education, and so on. Okay. Now, what about if we've got a more complicated situation where instead of having just two categories, males and females, in the data sets we've got typically, unfortunately, we limit ourselves just to the binary classification of gender. In other cases, you might have multiple categories. So, for example, you might say that not only do people's wages depend on education, age, and on their gender, but it might also depend on the type of job they've got, their occupational category. And in this particular data set, we've actually got 3 occupations for people, whether they're managerial roles, clerical roles, or labourers. Simple classifications. So we're tempted just to put in like category 1, 2, 3 for these, aren't we? But that wouldn't make any sense because these aren't counts of things, like, how many years of schooling have you had, 1, 2, 3. These are separate categories. So they don't compare 1 with 2, 2 with 3 in a linear kind of a way. So what you've actually got to do is create a set of dummy variables. You can only ever do things in 0, 1 effectively because these are categorical. So let's have a dummy variable. Let's first of all decide on what's called a base person. So we'll call a base person a person who's a manager. And then we'll put a dummy variable in that's equal to 1 if you're a clerical and 0 if you're not. And another dummy in that says you're 1 if you're a labourer and 0 if you're not. So if you think about that a little bit, you'll see about this probably if you can work through some of the tutorial exercises. Let's take a person who's a manager. They will not be a clerical worker and not a labourer. So the clerical will have a value of 0 and the labourer will have a value of 0. If they're a clerical worker, then the clerical will have a value 1 and labourer will be 0. If they're a labourer, it'll be a 0 and a 1. So you've got 3 categories, and you can represent those 3 categories by either a 0, or a 1 and a 0, or a 0 and a 1. So you only need 2 variables to capture 3 categories. Okay, so that's kind of the mathematical reason why we can do that. Interpretation is a little bit even easier for us to get our head around. Here's the model where we put in these 2 variables. And now we've already talked about the female dummy, but now let's have a look at the clerical and the labourer dummies. These things, if you think about the interpretation, it's not dissimilar to how you look at a 0, 1 binary categories, here multiple categories. The category that we're comparing with in each case is managers. So let's take 2 people. One's a manager and one's a clerical job. The clerical person will earn $10,000 less on average for the same level of education, age and gender. Now let's take 2 people. One's a manager and one's a labourer. The labourer will earn $6,700 less than the manager. Okay, so in each case, these dummies here equal 1 for this category or 1 for this category. They're compared with the base category, which is managers in each case. Okay, so you get a clear ranking here that both of these are negative, which means managers get paid the most. Funny enough, labourers get paid more than clerical workers. So some types of manual labour actually do, people earn more than what they do, those who sit in offices and push pens. But of course, to be a manager, it puts you in the highest paid position. Okay, so that's the interpretation of a multiple category dummy. And there's a little bit of explanation of that at the bottom of the previous page there, where we have the interpretation for clerical workers, and the top of this page here, where we look at the interpretation for labourers. Okay, now lastly, I just wanted to make a couple of comments about regression. When you look at regression output like this, it's all a bit complicated and messy, and clearly the last thing you want to do if you're running a nice report or giving a presentation in a as you'll be doing for your group project, is you just don't want to dump a Excel piece of output out like this. A whole lot of stuff that's gobbledygook numbers, too many decimal places and everything else. So there's a bit of work, a lot of statistical work is about communication. This is a really interesting model here. It tells us a lot about how wages are determined, influenced by personal characteristics and by the type of job you've got. but it doesn't present well in this simple form here. You've got to make it, or this sort of messy Excel output here, you've got to make it interesting. So first of all, get rid of the rubbish that you don't need. Only carry the essential information. So the coefficients are the most important information. So make sure that you highlight this column here. These are the numbers that tell you how much this slopes in the line, so they tell you how much things vary. So you must include those numbers there, but don't go including them with 6 decimal places like they've got here. Who cares if it's 715.1.219391 for gender effects? Just try 7151 would probably be totally adequate in this case. No need for any decimal places. Sometimes you need a couple of decimal places, depends on the nature of the data. Make a decision, but make it look nice and easy for people to understand and get their head around. So think about decimal places, get some information in there about accuracy. So I would say it's almost always a good idea just to throw in both the coefficients and the p-values. In this case, all the p-values are tiny, so every one of these variables really matters in explaining wages. So putting in p-values, but then also give us the r-squared, so we get some idea about how accurate your model is, and perhaps the standard error as well. Okay, so that's those things there. And then just think a little bit about how do you get your message across. So one of the things you might do in this case, for example, is you might say, let's take a typical person. We've got a 25-year-old female who has university education and is working as a manager. What does the model predict their wage would be? So plug some numbers in and tell us. Now then say, let's take a 25-year-old male who's got the same amount of education working in a manager as well. How much do they earn? So use that simple thing to communicate the ideas. So that's what we mean about that last point, about a little bit of flexibility, because when you're interpreting results, explaining results, you are telling a story for a purpose of communicating some ideas. And so you've got to be a little bit creative sometimes in getting the message across. Just a boring table of numbers may not do the job for you. Okay, that's it for this one. Thank you very much.